The second component of what we have to understand before we really get into the specifics of hypothesis testing is understanding this thing we call p-value. The first thing we had to understand was, first of all, sampling, p-value, and the next after this will be confidence intervals. And then we'll put this all together to understand how tests of differences are actually done. Well, whenever I think of p-values, I think of Macbeth. To p or not to p? That is the question. What is this thing called p-value? Now, one of the things I'm going to do in this module is probably dispel a few myths. If you've had a basic statistics class, you most likely have learned p-values in a very wrong way. And so what I want to do is be somewhat specific about this and then give you a caveat or a warning about how to use these in terms of decision making. So what we're going to do is we'll present some graphical descriptions of p-values showing the alpha risk and the beta risk explained in terms of overlapping probability distributions, which for the sake of illustration, we're just going to use a normal distribution. Now I want you to remember one thing. Rarely in nature will you find a normal distribution. Almost all distributions that you work of as an industrial engineer will have a long tail. This is called an Erlang or a Poisson distribution. And so that long tail, usually we see the behavior we want is peaked and the long tail is the behavior we don't want. That's the loss function that we take a look at in processes. So what do we see? Well, in this graphic you see this normal distribution. And we see there's a vertical line, which is the probability level. And this is usually a decision criteria. So if I say I want to have 5% in terms of risk, then I would draw this line based on the amount of data under the curve. So the data under the curve is going to be nominalized to equal to 100% if you will. And then the amount of data under the curve to the right is the p-value. This is the probability of an event occurring. Usually when we talk about an event, we talk about a failure event. 1 minus p is the rest of the distribution. That's the probability of an event not occurring. And so when the p-value is very small, it's a rare event to get that type of occurrence or that type of failure. So what we say is that it's less likely that that small p-value will happen by chance. So we're talking about a p-value of 0.05. That's a 1 out of 20 risk that we would get something smaller than that happening just by chance. Or if you alternatively talk about it, it's a 95% chance that we would get something on the other side of that just also happening by chance. So when we take a look at this, what we see is the p-value is actually this area under the curve, and what we have is the population is a distribution. The center of that population would be like our null hypothesis, we call that H sub O, and we would say that center of the distribution is the population mean. So the question is, how far is the sample mean, x bar, from that? And at what point in time would we say it's no longer likely to come from the same distribution as that population? So that's really what the p-value is trying to tell us. So if we take a look and we say, okay, alpha is the risk of finding a difference when there isn't one. So this is the risk to the producer. Beta is the risk of not finding a difference when there really is one. In other words, we ship the bad product to the customer. Now what we see is, I have two hypotheses here. H sub O is the red distribution, and that is my null hypothesis. That's what I think is happening. And the question is this other hypothesis, the blue one, H sub A, the alternative hypothesis, is it different? And what we see is I have this vertical line, and that vertical line is the amount of risk I have relative to A. But we see that A, there is actually blue data above it that is from the second or the alternative hypothesis. But that is how far away, as if you will think of it this way, the red distribution can shift before you detect the difference. Now, beta, though, is the amount of distribution of the blue data in the red distribution that is just happening by chance. So if I get data in this blue distribution, in that beta area, I can't tell is that the red distribution or the blue distribution, just as I can't tell the other. So how do we think of these types of risks? Okay, so p-value is giving us a probabilistic answer. And the question is, if the null hypothesis, H sub O, is true, how likely would we see a sample this far away in terms of magnitude, or even larger, just by chance? So the smaller the p-value, the more evidence against the null hypothesis that's being provided by the data. So what we suggest, even though is not technically 100% correct from a statistician's viewpoint, is that the p-value is the probability that the null hypothesis, H sub O, is true. So what we want to do is figure out what is actually going on in the process. So how rigid do we have to be in interpreting p-value as a decision criteria of significance? If 0.05 is the rejection criteria, and we say that it's not, what about 0.06 or 0.07 or 0.1? Should we reject those also? So what we start seeing is that the statisticians have realized that interpreting p-values as more and more people are using statistical tools, there's some warnings that have to be given. As George Box, one of the most eminent statisticians of our time, had said, all models are wrong, but some models are useful. And we see just this year, in 2016, when we recorded the video in March, the American Statistical Association has released a statement on p-values in the American Statistician. This slide summarizes the 6 points that they make. First, a p-value can indicate how incompatible data are with a particular statistical model. And so it says the data is not from that model, p-value less than 0.05. P-values do not, though, measure the probability studied is the hypothesis true, or the probability that the data were actually produced by random choice. We have no idea. So we have to go back to understanding how the sampling plan was done. Scientific inclusions and policy or business decisions should not be based on p-value passing a threshold. It has to be more than that. Are we measuring the right thing? Are we asking the right questions? Did the data actually tell us something? Is it really from the population we want to take a look at? So the p-value is not just a final determinant. Anytime we see a 0.05, we have a difference and therefore we should use it. We have to really think through all the engineering details that go into this particular problem we're analyzing. So proper inference about the future requires full reporting of all the components, including the beta risk, and transparency so that a decision maker can see what actually is the set of total risks we're seeing, what was the sample size, what is the basis on which we're making this judgment, and how solid is the choice that they're being asked to make. So p-value, or statistical significance, doesn't really measure the size of the effect or the importance of a result. Again, we have to take a look at the physical dimensions, and we have to take a look at the knowledge that we gain from the process, the profound knowledge that's generated about what future states could be based on the whole picture. So the conclusion is, by itself, a p-value does not provide a good measure of evidence regarding a model or a hypothesis. We have to have a much more comprehensive systems approach view towards understanding. And this is why we've taken our time very sequentially to take a look at each of the different components about how we make a judgment with a hypothesis test. It has to be anchored in the physical world, the hypothesis we draw. Sample size has to be the right size, and it has to be done so that we balance the alpha and beta risks between the consumer loss and the producer loss. We have to then have a p-value that does indeed make some sense for a decision criteria that makes sense. And then we have to choose the test. What sort of difference is it that we're interested in testing? So we're going to continue with this pursuit of understanding the components of hypothesis testing in our next video.